Lab 2 of Falling Object. In this lab we will attempt to model the y-axis position versus time of a falling object. The first model will include only the force of gravity with F net. The second model will include both gravity and the turbulent drag forces. We'll review both models to show how they match up with the observed motion of the falling object. Our models will be based on Newton's second law, shown here, where we will utilize F net equals the weight force with the equation shown in the first model, and F net equals the weight force plus the turbulent drag force with the appropriate equation shown following. We'll then use the velocity versus time of each model and show that only the model including the drag force predicts the terminal velocity for the object. Finally, we will show that the terminal velocity of an object thrown towards the Earth, as opposed to a free-falling object, will over a long enough time period have roughly the equivalent velocity, or terminal velocity. Here we see our video of an object falling towards the Earth. We'll play that. And we'll see that on the top right hand of the screen, the graph shows the change in the y-axis over the change in time. Now we'll take a look at our Python code utilizing just the gravitational force. We'll see right here that we use the gravitational constant 9.8 meters per second, and we'll also see that if we scroll down a little bit here, that our loop will contain the final time, will also contain the weight force equation, and the F net is only equivalent to the weight force, shown by the equation here, the mass times the gravitational pull times j hat in the negative plane. We'll also see Newton's second law here written out, same as in the first lab. And then we will also see the position change of the ball with regards to velocity over the change in time. Next, we're going to see the drag force added to this. So we have the proportional constant for the drag force, B. What we did is we took the final point in our video and we fit the drag force constant to make that point fit. Here we have the while loop again. We have the same equation for the weight force, but now what we've done is we've broken out the drag force into its component forms. We've got the drag force hat, which is always the opposite of the ball's velocity. And then we've got the magnitude of the drag force, which in this case we used it being proportional to the square of the velocity of the ball. And we take the total force to equal the components, the magnitude times the FD hat. And what we'll see here is that we have it graphed with the position over time for just the gravitational force in the blue, and then we also have the position over time with the drag force and the gravitational force shown in the yellow, with our red position showing the actual object in motion. What we see is that the falling object looks like it follows pretty well with the position of drag plus gravitational pull. I think there was some possible error in the tracking, which is why this does not fit perfectly. Next, we'll take a look at the velocity over time. First, with just the model containing the gravitational force, we'll see that the velocity continues in a linear fashion upward over time with just that force. Next, we'll take a look at the forces of gravity and drag put together, and we will see that the speed, or the velocity I should say, actually starts to trail off over time and not continue into infinity. If we compare the two results of these graphs, we'll see that both the graphs look different, and also the final velocity over time is much smaller for the second, showing that there is an approach to terminal velocity. We'll now see a graph of velocity versus time for an object thrown or dropped, and that'll go right along with our terminal velocity from the previous step. We'll see that the drop actually increases in velocity and then over time levels off, and the thrown object decreases in velocity over time, but then also levels off to approximately the same velocity. This shows us that there is a terminal velocity for both dropped and thrown objects. Thanks for watching.